Welcome back. In this third tutorial, Ken will demonstrate in detail the tools and concepts you need to know to correctly make a single image magnitude measurement using the necessary quality control methods. This is the only tutorial which will run longer than the others.
Thanks, Stuart. From the available image page, where I've filtered my list to show the BLCam images we're using as an example in this tutorial, for the single image I want to measure, I'll click on the blue hyperlink for the first BLCam image. This brings me to the image analysis page. First, I'll do a full zoom out to inspect the image for things like clouds, moon illumination irregularities, passing satellites, and imperfections around the edge of the image, etc. The lines visible on full zoom out are not a sign of poor image quality. They're just an artifact which disappears as we zoom in. We can see which way north is oriented at the bottom right. We'll see later that this will be useful to know when we go to create charts to compare the image to in order to ensure the target is correctly identified. As we move the mouse across the image, the right ascension and declination coordinates automatically change according to the position. This can also help us during the target verification process. Now we download all the variables in the GCVS catalog by mousing over Catalogs and clicking GCVS. Clicking AAVSO comp stars will download this data onto the image. The stars are listed to the left, showing signal to noise ratio, SNR, and full width half maximum, FWHM. These are basically values which indicate how strong the signal is from the star and how good the image quality is in the area. The higher the SNR, the better. If we wanted to download SIMBAD data for everything in the field, just click the Load SIMBAD Data link. The red-colored SIMBAD data can be accessed by left-clicking the object. SIMBAD is another catalog of stars useful when doing research or finding other data not listed in the GCVS. To remove this data, click Clear SIMBAD Data from the catalog drop-down list. Targets from the GCVS catalog are colored green, comp stars are colored blue. The color code for check stars is orange. Any star which is overexposed and which saturate the image are unusable and colored gray. For advanced users, the program defines this at an ADU of about 55,000 or greater. Photometrica automatically excludes such stars from the analysis, be they targets or comp stars, whether or not you delete them. This star has a value of 120 or 12, which means its V filter magnitude, roundest to the nearest tenth, is 12.0. We see the magnitude taken to 3 decimals in the V filter box here as 12.044. This particular image was taken with an R filter, as we see here, so the R magnitude of 11.685, which will be used in the analysis, is noted in the R filter box. There are also boxes for B and I filters. If we want to change what the star is called, just type in the box and click Update. We also see the exact RA and DEC, SNR, max ADU, and other information more advanced observers will recognize. We'll go over data the details link will show us later. We can delete data we don't want on the image by either clicking Delete from the details box or clicking the X next to the object to delete from the list. If we want to find a target in the list on the image or in the pan area on the lower left, click the binocular icon and a red flashing box will appear in the centroid of the object we're trying to locate. We'd like to use comp stars with an SNR greater than 100 if possible. We can set the program to exclude stars with an SNR below a certain value by going to Tools, Settings, and entering the value we want. The setting will apply the next time we download data onto the image. Often though, it won't be possible to get comps that good, so as a beginner you might want to leave this on the default setting of 20. One could do a measurement of a single image with only one comp star. However, the accuracy of the measurement can be tracked by adding a check star. That way, when the target's magnitude is measured, the check star, whose magnitude is known, will be measured at the same time. If the magnitude for the check star is close to its known magnitude, that's a good indication that all is well. You can improve accuracy but perhaps increase error rates by using more than one comp star. Such a measurement is known as an ensemble. If more than one comp star is used, having a check star is mandatory. Not all comp stars are the same in terms of statistical accuracy. Some have a higher error rate than others. We'd ideally like to use comps with an error rate less than 0.015 and no greater than 0.02. To check the error rate for the comps in the field, go to Catalogs and click Show AAVSO Sequence. That will open up a new window with a list of the comp stars in the field by filter and their error value in parentheses. So now I'll pick 3 stars, of which 2 I will use as comps and 1 for a check, which have an SNR greater than 100 if possible and an error rate of less than 0.02 if possible. If no stars meet these 2 criteria, I'll choose the 3 which come closest. Since this measurement was done with a red filter, we'll look in the column for the red filter marked RC for the error rates in parentheses. I see that stars 11.4, 12, and 12.3 are the 3 brightest stars with the lowest error rates as shown here. I also see that their SNR is greater than 100, so these are the stars I will use for the measurement. Other factors we might want to consider include keeping the stars we choose close to the target, and we'd like to avoid having other bright objects right next to the stars we choose. For quality reasons, nothing we use in the analysis should be too close to the edge of the image. So now I'll eliminate the stars I have not chosen. To enable me to do that quickly, especially when there are a lot more comp stars than we see here, I'll find the comp stars I want to keep by using the binoculars and temporarily change them all to check star orange. Having done that, I can just quickly delete anything left in the list which is not orange or green without thinking. Finally, I changed 2 of the 3 stars left in orange back to comp stars, which leave us with the desired 2 blue comps and an orange check star. Now we're ready to set the aperture or innermost circle. Once we do that, the same setting will be applied to all stars in the field. The rule of thumb is to set the aperture to 1.5 to 2 times the average FWHM of all the stars, closer to 2 for bright objects and closer to 1.5 for dim objects. So based on that rule, I'll set the aperture to 3.7 by clicking the Change button next to Aperture Radius. We could bring up the same box by selecting the Tools drop-down menu and selecting Aperture and Sky Annulus. Once I've entered the desired setting, I click Apply and then Hide to close the box. If there are bright stars within the outer 2 circles, or sky annulus, that is undesirable. In most cases, the program's default setting should automatically remove such outliers. But especially if there is a very bright object close to the target, comp, or check star, it's best to manually change the radius and width of the outer 2 circles, again known as the sky annulus, so that the bright object is excluded. Let's use this star as an example. Click on the star and change the annulus radius and width to lower values. Lowering the width value decreases the size of the outermost circle. Lowering the radius value decreases the size of the second middle circle. Use trial and error to get values which will eliminate a bright object, but leave the circles as wide apart as possible. These adjustments can be made for each star individually, so what you set for one star doesn't have to apply to all stars, as was the case with the aperture. In this case, I'll change the sky annulus radius to 5 and the width to 3 and click Update. More often than not, it will not be necessary to do this. You need only make this adjustment when very bright objects are involved.
Great, Ken. Thanks. In the next tutorial, Ken will cover how to ensure the target has been correctly identified and how to check for contamination near one of the analysis objects. Thanks for listening.